Hi, today we are going to discuss in detail the Bohr's model of hydrogen atom. Let us first recall the idea of spectrum and the electron energies. So spectrum is created when electron jumps from one orbit to another. Either it gives up or absorbs photons, and this is a result of energy difference. And the different orbit has different energy level. And also, the photon wavelength is determined by multiplying the Planck's constant h times the frequency. And the total mechanical energy, meaning the electron energies here, is the total of the electric potential energies and the kinetic energy. And also, we learned from the previous discussion the energy level of a Bohr model. So this is given by this equation 1. So our energy level is negative E squared over 8 pi epsilon naught Rn. And Rn here is the orbit of Bohr or Bohr's orbit. So if we substitute these Bohr orbits to this equation, so we can get this equation, the equation 3, where this constant is equivalent to E1, and our E1 is equal to negative 2.18 times 10 to the negative 18 joule, or negative 13.6 in electron volt. So our energy level can be given by this equation. Energy level is equal to negative E1 over n squared. So here, this figure shows the first three orbits of a hydrogen atom. So this is the first orbit, the second orbit, and the third orbit. So n here is the quantum number. Okay? So the quantum number here, n is equal to 1, n is equal to 2, and n is equal to 3. And also, we can call this as the ground state, the first excited state, and the second excited state. And this figure, this is the visualization of the electron waves for the Bohr orbits. And for the energy levels, so this is the energy level of a hydrogen atom. So as you can see, these levels are all negative. So the energy here are all negative. This is the energy in joules, and this is the energy in electron volt. So meaning this negative 21.76 times 10 to the negative 19 joule is equivalent to negative 13.6 electron volt. Okay? So what does this negative sign means? So this signifies that the electron does not have enough energy to escape from the nucleus. So an atomic electron can have only these energies. So meaning if we can liken this to a person on a ladder who can stand only on its steps and not in between. Okay? So here, this is the lowest energy level, the E1. And this is called the ground state of the atom. And this one, the higher levels, this is the E2, E3, E4, and E5, and these are called excited states. So again, as what I have said, that n here is the quantum number. So if you notice, as we increase the quantum number and it goes to infinity, our energy becomes 0. And the electron is no longer bound to the nucleus to form an atom. So if this becomes positive, it becomes a free electron. And this positive energy for a nucleus electron combination means that the electron is free and has no quantum conditions to fulfill. So as what we have learned from our basic concept of physics, the work. So the work needed to remove an electron from an atom in its ground state is called its ionization energy. So the ionization energy is equal to the negative E1. And this is the energy that must be provided to raise an electron from its ground state to an energy of 0, meaning our energy becomes 0, meaning when it is free. So in the case of the hydrogen, the ionization energy is 13.6 electron volt, since the ground state energy of the hydrogen atom is equal to negative 13.6 electron volt. Now let us have the first sample problem. So let's check if we understood the concept of the energy level. So here, an electron collides with a hydrogen atom in its ground state and excites it to a state of n is equal to 3. So if the ground state, if we have the ground state, meaning n is equal to 1, and it excites, meaning it jumps to n is equal to 3. How much energy was given to the hydrogen atom in this inelastic, meaning the kinetic energy is not conserved, collision? So here, the given, the initial state is in ground state, meaning n is equal to 1. The final state is n is equal to 3. So we need to find the energy change of the hydrogen atom. So delta E, meaning the change of energy, is equal to final energy minus initial energy. So the final energy is given by this E1 over NF squared, meaning the final state, minus E1 over the initial state squared. So we can have this E1 here. This is the common factor. So this is 1 over NF squared minus NI squared. Note that E1 is equivalent to negative 13.6 electron volt. So delta E is equal to negative 13.6 over 1 over 3 squared, 3, n is equal to 3 for the final state, and n is equal to 1 for the initial state. So we can rewrite this as negative 13.6 electron volt, 1 over 9 minus 1, and this is equal to negative 13.6 electron volt times negative 8 over 9. And this is equal to 108.8 over 9 electron volt, and this is equivalent to 12.09 electron. For our second sample problem, we need to find the wavelength of a photon that will be absorbed if an electron is to raise in a hydrogen atom is raised from n is equal to 3 state to the n is equal to 5 state. So the given here is the initial state is equal to n is equal to 3, and the final state is n is equal to 5. So we need to find the wavelength lambda. So let's recall that the change of E is equal to Planck's constant times the frequency. And the frequency, we also have this relationship of the speed of light, the wavelength, and the frequency. So if we need to find the wavelength, lambda is equal to C over S. Okay? So this constant C. Delta E is equal to final energy minus initial energy. So we can rewrite this again into this form. So E1 over NF squared minus E1 over NI squared. And this is equal to E1 times 1 over NF squared minus 1 over NI squared. So our delta E, recall, E1 is equal to negative 13.6 electron volt. So our N is equal to 5 in the final state, and our initial state, N is equal to 3. So this can be, this becomes negative 13.6 electron volt times 1 over 25 over 1 over 9. So here, we just need to find the LCD, negative 13.6 electron volt, 225, 9 minus 25. So this is equal to negative 13.6. So this becomes negative 16 over 225. And this is equivalent to 0.97 electron volt. So finding the wavelength, delta E is equal to Planck's constant times F. And we solve the delta E is equal to 0.97 electron volt over H. So we can find the frequency. So recall again that the 1 electron volt is equal to 1.602 times 10 to the negative 19 joule. So we need to convert the 0.97 electron volt, this is delta E, into joule. Why? Because H here is in terms of joule. So 0.97 electron volt, so 1 electron volt, 1.602 times 10 to the negative 19 joule. So cancel the electron volt. So this is equivalent to 1.55 times 10 to the negative 19 joule. So F here is 1.55 times 10 to the negative 19 joule. So again, this is the equivalent of 0.97 electron volt over H. This is 6.626 times 10 to the negative 34 joule times seconds. So cancel the joules. So we have a remaining 1 over second, and that is the unit of frequency, and that is equivalent to hertz. So 1.55 times 10 to the negative 19 over this one. So we have 8.345 times 10 to the 14, 1 over second, or hertz. So now for the lambda, this is c over f, where c is a constant. This is the speed of light. This is equivalent to 3 times 10 to the 8 meter per second over the frequency that we've obtained here. So our lambda is 1.28 times 10 to the negative 6 meters. Thank you for viewing and for bearing with my handwriting. And I will see you again for our next lecture. See you!